Welcome back for our first video in our bonus content for ordinary differential equations. This is a subject matter that would be covered in a more advanced differential equations class. Your teacher, if they have time, may try to make it into this chapter for you. It's not part of the core content for the class that the college normally offers it as a 200 level course. But I wanted to go ahead and show this to you, as this is the main missing piece that we were trying to build up to. So you should be able to understand this after you have had a little bit of linear algebra on top of what you've done so far in differential equations. I have put the linear algebra videos up, and one of the last things that we talk about in linear algebra in the chapter 7 videos is eigenvalues and eigenvectors. Those will be coming up here shortly in this chapter. So that's why you need that content first. But let's see what happens when we have a system of first order linear differential equations. And this content from 8.1 is just some preliminary theory behind linear systems of differential equations. So we're going to start off with a system written as dx dt is equal to 3x minus 5y, and dy dt is equal to 4x plus 8y, and the instructions tell us to write the system here in matrix form. So these differentials, I'm going to write that as the derivative of capital X. Those are my derivatives of x and y with respect to t, and I'll just call that capital X prime. And on the right-hand side, I'm going to write my coefficient matrix, and I'm going to use parentheses like the book does. I like the brackets more often. I might accidentally switch to those. And then my variable matrix X, where capital X is equal to my variables in play here are X and Y. So if I would use matrix multiplication, like we learned about in linear algebra, and expand this out, I would get this system of differential equations that we have right here. Let's try another one, number 3. And it says dx dt is equal to negative 3x plus 4y minus 9z. It says dy dt is equal to 6x minus y, and there's an implied plus 0z there, and dz dt is equal to 10x plus 4y plus 3z. So I'm going to change this into capital X prime is equal to, and my coefficient matrix here is negative 3, 4, negative 9, 6, negative 1, 0, 10, 4, 3 times capital X, where capital X equals the matrix X, Y, Z. All right, those are pretty straightforward. Let's move on to one that has a little extra added to it. Let's look at number 5. And number 5 says that we have dx dt is equal to x minus y plus z, and now we've got plus t minus 1. So remember, we're differentiating with respect to t. So these t's are going to be extra things that need to be added on at the end. dy dt is equal to 2x plus y minus z, and then minus 3t squared, and dz dt is equal to x plus y plus z plus t squared minus t plus 2. So that's quite a bit there to go from nothing to that. So let's go ahead and write down my x prime on the left and coefficient matrix for x, y, and z. 1, negative 1, 1, 2, 1, negative 1, 1, 1, 1, and then times x, y, z is capital X here. And that's the easy part. Now we need to look at our t squared pieces. So we have 0, and then we have negative 3, and then we have 1 t squared, and then we have our t pieces, 1, 0, negative 1 t, and then we have our constant pieces, negative 1, 0, 2, where my capital X is equal to x, y, z. And let's look now at number 7. 7 asks us to write the given linear system without the use of matrices. So we're going to start off with capital X prime is equal to 4, 2, negative 1, 3, capital X plus 1, negative 1, e to the t. So that's dx dt is equal to 4x plus 2y, and then plus e to the t. 1 e to the t goes with this first equation up here. dy dt equals negative x plus 3y minus e to the t. All right, they don't tell us what variables are inside of x, but we just assume it's x and y, and that we do know that we have a t as our independent variable over here. We see that. So let's go ahead and let's look at number 9. I'm going to give myself a little bit more space. 9 says d dt of x, y, z. They're a little more explicit here. Is equal to 1, negative 1, 2, 3, negative 4, 1, negative 2, 5, 6. And then we have x, y, z. Then we have plus 1, 2, 2, e to the negative t plus 3 negative 1, 1 t. So that's a lot to even write on the whiteboard, but we're going to write that in a form without any matrices. So this is going to be dx dt, dy dt, and dz dt. This is going to be x minus y plus 2z. This is 3x minus 4y plus z. And this is negative 2x plus 5y plus 6z. That takes care of the coefficient matrix times the variable matrix. Now I have an e to the negative t, a 2e to the negative t, and a 2e to the negative t. And then I have 3t minus t and plus t. So 1, negative 1, 2, 1, that's supposed to be a oh, there's a minus sign here. That's tricky. So this is minus, plus, and minus. So watch out for that. If they put a minus sign out front of the matrix, change it to addition and change the sign of everything in the matrix so you don't make a sign error like I just did. So that's minus 3, and then we have 3, negative 4, 1, 2, 1. We have negative 2, 5, 6, 2, negative 1. Perfect. That was number 9. Let's move on and look at number 11 from the book. And the instructions change there and say that we are to verify that the vector capital X is a solution of the given homogeneous linear system. Homogeneous meaning that it is equal to 0 vector. So 11 is dx dt is equal to 3x minus 4y, and dy dt is equal to 4x minus 7y, and we're told that we want to test capital X is equal to 1/2 e to the negative 5t. So x prime, when we differentiate this, is going to be a negative 5 e to the negative 5t. So multiply the insides here by negative 5. Keep the e to the negative 5t for the x prime. And that's going to be that we want to test is negative 5 e to the negative 5t. Is that equal to 3 times e to the negative 5t minus 4 times 2 e to the negative 5t. So that is 3 minus 8 is a negative 5 e to the negative 5t. So check. And the bottom row is negative 10 e to the negative 5t. Is that equal to 4 times 1 is 4 e to the negative 5t. And negative 7 times 2 is negative 14 e to the negative 5t is a negative 10 e to the negative 5t. Check. So yes, x equals 1, 2 e to the negative 5t is a solution. to the given system of linear first order differential equations. Let's go ahead and wrap up here with number 13. 13 has x bar, or I'm sorry, x prime equals, and then we have -1, 1/4, 1 -1, x. X is equal to -1, 2 e to the -3t over 2. So that means x prime equals, and I need to multiply by -3/2 on the inside. So this is 3/2 and -3 e to the -3t over 2. And let's see if that's the case. When I multiply here, 3/2 -3 e to the -3t over 2, is that equal to -1, 1/4, 1 -1, -1, 2 e to the -3t over 2. So let's do matrix multiplication on the left and see if it comes, or on the right, and see if it comes out to be what's on the left. So -1 times -1 is 1. And then 1/4 times 2 is 1/2. 1 times -1 is -1. -1 times 2 is -2. E to the -3t over 2 is equal to 3/2. -3 e to the -3t over 2. So check, they're equal. So yes, x equals -1, 2 e to the -3t over 2 is a solution. All right, that's it for this video, and we'll come back next time and talk about 8.2. And we'll start looking specifically at 8.2.1, which are solutions that have distinct real eigenvalues to them. So see you for the next video. If you don't know about eigenvalues and eigenvectors, go ahead and take a look at the linear algebra video, chapter 7. You need to have an exposure to linear algebra and eigenvalues and eigenvectors before continuing here in chapter 8 and using the methods to solve these differential equations, though it's going to go back to a lot of the things that we did with homogeneous linear first order differential equations, and where we did the m substitution, and we got different values of m, and we ended up with a yc, and then if it was non-homogeneous, we ended up with a yp, and we did the superposition principle with y total is equal to yc plus yp. We're going to do the same thing here, but we're going to get a capital X sub c and a capital X sub p, and we're going to add them together to get the total solution as needed. Starting off talking about some homogeneous systems that all equal the 0 vector, and then moving to some non-homogeneous systems. And so 8.2 will be homogeneous, and 8.3 will be non-homogeneous. All right, see you for the next video.